All right, guys, we're almost done here for the day. We are on the section 8-4 test review. This is the last section that will be on the chapter 7 and 8 test. So, of course, this is due Wednesday, the 8th, for bonus points. Okay, so number 1 says, the Environmental Protection Agency has determined that safe drinking water should have an average pH of 7 moles per liter. You are testing water from a new source and take 30 vials of water. Water is unsafe if it deviates too far from 7 moles per liter in either direction. The mean pH level in your sample is 6.4 moles per liter, which is slightly acidic. The standard deviation of the sample is 0.5 moles per liter. Okay, so also, I really don't know if these values are correct. I'm just getting them from a template. They could be totally wrong, but this is the idea of what we would do if we for sure knew the right values of how many moles per liter of pH, blah, 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 we needed in our water. So let's kind of summarize what was important. The EPA has determined that safe drinking water should have an average, so a mean pH of 7 moles per liter. Okay, I'm already thinking that's probably my claim. If this is what's safe or if this is what's normal or blah, 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 that's usually my null hypothesis, my claim. Now we're testing water from a new source and we take 30 vials of water. Okay, so I'm thinking that's my sample. And then it says water is unsafe if it deviates. Deviates mean different from in some way, greater or less than, too far from 7 moles per liter in either direction. The mean pH level in your sample is 6.4. In your sample is 6.4 moles per liter. I guess I'll underline that whole thing. That's going to be my sample mean. Okay, so I'm already thinking X bar is 6.4 moles per liter, which is slightly acidic. The standard deviation of the sample is 0.5. Okay, so that's my S. S is 0.5. All right. Do the data provide convincing evidence? There's that sentence that tells us we're doing a hypothesis test. At the alpha, they tell us alpha equals 0.05 level, that the true mean, here comes my parameter, true mean pH of water from this source differs, I'm going to change color, this is so important, differs from 7 moles per liter. That word, differs, tells me that I'm going to do a two-sided test. And I know two-sided tests have been throwing you off, so we're going to go over one here. Differs from 7 moles per liter. So again, this part tells me what I want my alternative hypothesis to be, not equal to 7, which means my null must be equal to 7, which is what I was thinking from up here. Okay, so let's follow that 4-step process. Remember, we need to state the parameter, statistic, hypotheses, and significance level. So let's see. Our state step. First, I start with my parameter. I'm talking about the true mean, so that will be mu is equal to the true, and I'm just going to copy it down. True mean pH of water from this source. That is directly from the question. And then I was told that X bar is equal to 6.4 moles per liter. I also know that S is equal to 0.5 moles per liter. And then I need my hypotheses. So the null hypothesis, again, is going to be the normal baseline situation. So that would be that the water is safe, or that the true mean is equal to 7 moles per liter. On the other hand, my alternative is going to be that it's different from, right? It didn't give me an indication either way, whether it's greater or less than. It just wants to know if it's different. So I'm going to use mu is not equal to 7 moles per liter. And then I need to state my significance level. So alpha, it said, was 0.05. That was part of the question as well. Okay, so moving on to the plan step. Hopefully you're remembering now that this is where you state the name of the test and check the conditions. The name of this test, the name of the appropriate inference method for means, is a one-sample t-test for mu. So one sample, I don't need a hyphen there. One sample t-test for mu. And then I check my conditions. So first is the random condition. So it says they take 30 vials of water. It doesn't actually say that they're random, but I think just from the idea that the water is moving, we can assume that those 30 vials are random. So assume 30 vials are a random sample. Okay, condition met. Number 2 is the 10% condition. So my n equal to 30. Is that less than 1/10 of all vials possible from this source? Okay, so 10 times 30 is 300, and vials are pretty small. So I think you could take 300 vials of water from pretty much any water source you're talking about. So that condition is met as well. Okay, the third condition is the normal condition. So remember, this is not a proportion, so I'm not going to be doing large counts. I have 3 different ways to meet this condition. My population distribution can be normal. N can be greater than or equal to 30 so that the CLT applies, or my sample distribution can show no strong skew or outliers. Again, just to give you a hint, if you don't actually have sample data, you can't use the third way to prove or to show this condition. We don't have sample data here. So we're hoping one of the first 2 fits, and in this case, n is 30, so the CLT is going to apply. N is equal to 30, which is greater than or equal to 30. So the CLT central limit theorem applies. Check. Okay, conditions are met. We're ready to move on to the do step. Again, we start with our general formula for the test statistic. This is the statistic minus the parameter divided by the standard deviation. Okay, so for means, the test statistic is not a z-score anymore, because this is not a normal distribution anymore. It's a t-distribution because we'd have to estimate the population standard deviation with the sample standard deviation. So we're going to use that t equals statistic x bar minus parameter mu divided by standard deviation, or standard error, s divided by the square root of n. Okay, so t is equal to x bar minus mu divided by s divided by the square root of n. Okay, so we're ready to fill in our values to that. So x bar, we said was 6.4. 6.4 minus our hypothesized value for mu is 7, the parameter, divided by s, which is 0.5, divided by the square root of n, which is 30. Again, if I put parentheses around my numerator, I can type this all in one command, which is what you want to do to make sure we limit rounding error problems. Okay, so parentheses 6.4 minus 7, and my parentheses, divide by 0.5. Oh, actually, I almost forgot. I do also need parentheses around the numerator here to make sure that I divide by all of this. Otherwise, order of operations, we'll take the difference in the top divided by 0.5 and then divide that value by the square root of 30, and that's not what we want. So again, put parentheses around the bottom as well. 0.5 divided by second square root of 30. And, oops, put my 30, or end parentheses outside of the square root. All right, I get negative 6.57 if I round to 2 decimal places. This is negative 6.57. Okay, so already, actually I'm gonna write it in this step below. Already I'm thinking with a z-score, or sorry, it's not a z-score, it's a t-value. With a t-value that large, this is probably going to be a very small p-value. This means that my sample mean of 6.4 is 6.5 standard errors below, because it's negative, below the mean. So let's sketch that picture really quick. Before we can sketch the picture though, we do need to know our estimate for the standard deviation for x bar. Remember, we use the standard error to estimate that. And that's my s divided by the square root of n. So what is 0.5 divided by the square root of 30? Let's find out. 0.5 divided by the second square root of 30. All right, 0.09, that's probably 2 decimal places is probably enough for the means because I was only given 1 decimal place for my sample mean anyways. So 0.09. Okay, so I sketch my t-distribution curve. Again, it looks like a normal curve, but there's a little bit more area in the tails. That wasn't a very good curve, but bear with me. So my center is my hypothesized mean, 7. Again, this is the t-distribution with degrees of freedom equal to 29, right? 30 minus 1 is 29. One standard deviation above the mean would be 7 plus 0.09, so 7.09. 2 would be add 0.09 again, so 7.18. Add 0.19 or 0.09 again, so 7.27. I know my multiples of 9, so I'm just adding 9 there. And then I have to subtract, so that'd be what? 6.91, and then 6.82, and then 6.73. If you want to check that again, you can add and subtract in your calculator. 7 minus 0.09, oops, just once. And then again, and then again. But that's what you get. Okay, so I can mark on here my actual sample mean I got. I want 6.4. 3 standard of errors below the mean is only 6.73, so I really need to go much farther out. That was 3, 4, 5, 6, 7. Okay, so my 6.4 is going to be somewhere between 6 and 7 standard errors beneath the mean. So it's going to be right about right here. And then the area underneath the curve at that point obviously is something super, super, super tiny, right? It's hard to even see. It's basically even with the horizontal axis at this point. But again, that is the probability that my sample mean is less than or equal to 6.4, which I'm pointing out again how this references the t-value. That's the probability that that t-value is less than or equal to negative 6.57. That's the probability I'm actually finding, but it's the same thing as this probability that I've drawn the picture of. Okay, so let's find that. We could use table A3 to find a range, but I'd really prefer you find the p-value by using that TCDF function. So let's see what TCDF asks for. Second distribution, I scroll down to TCDF, which is the 6th one. Ask me for my lower and my upper. So looking at my picture, my lower, this is a left area, so it's something really, really, really small, like negative 10,000. My upper is the right bound, which again is my sample mean of 6.4. Degrees of freedom are 29. Okay, so let's write down that that's what we entered. Negative 10,000, comma, 6. Oh, I'm sorry. I said 6.4 because that's my sample mean and I accidentally made a mistake. I really, again, want my t-value. With TCDF, we use the t-value. So let me go up and correct this. It should be negative 6.57. And again, I know my picture is showing the sample mean, but this would be the same picture just with different labels, same area for my t-value of negative 6.57. So fill that in, and then my degrees of freedom are 29 because my sample size is 30. 30 minus 1 is 29. Okay, so let's paste that in and see what we get. 1.689, blah, 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 e to the negative 7th. So that means I move my decimal place to the left because it's negative, so left 7 places. So if I move it once, I've got 0.1, blah, 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 blah. I have to move it 6 more times, so I have to fill in 6 zeros before the 1. So this is going to be 0.1, 2, 3, 4, 5, 6. 6 zeros, 1, 6, 8, 9. That is my p-value. And obviously that is very, very small. You could say it's approximately 0. Very tiny. Okay, so last step is to conclude. So we say since our p-value equal to 0.1, 2, 3, 4, 5, 6 zeros, 1, I'm just gonna round, 1.7, is definitely less than alpha equal to 0.05. Oh, you know what? I totally forgot something. That actually is not going to be my exact p-value. I have to remember here, sorry, let me erase real quick. I have to remember that this is supposed to be a two-sided test. And this is a super common mistake for students to make. If my hypothesis had just been mu is less than 7 moles per liter, this would be my p-value. But I actually want this to be just different from. So we say this far out or more or less, or on the other side, if it were that much greater than the mean. So let's see, 1, 2, 3, 4, 5, 6, 7. Somewhere out here, about 6.57, standard errors above the mean. So this tiny area. So it's this area plus that area. And I know this is kind of a poor example to demonstrate that because there's essentially no area under the curve at that point. But this does mean that to find our p-value, we have to take 2 times that 0.2345617. What would that be? Okay, that value times 2 is going to be 6 zeros and then 3 4, essentially. 0.12345634. Very, very, very tiny. Okay, so let me fix that. Since our p-value equal to 0.0000034 is less than alpha, we reject the null. Right, if our p-value is smaller than alpha, we reject the null. That means we do have convincing evidence. And I'm just going to go back up to the question to finish this out. We do have convincing evidence that the true mean pH of water from the source differs from 7 moles per liter. That the true mean pH of water from this source differs from 7 moles per liter. Oh, not liter, liter. Okay, so that's it, guys. We have finished our hypothesis test for a mean. So again, this was a two-tailed test, which means we have to multiply that original probability we get times 2. In our case, it didn't make it very much bigger, so it was still less than alpha, and we rejected the null, meaning that we did have convincing evidence. Okay, I'm going to do the problem on the back in the next video.